Okay, if you recall, last day we talked about apparent weight, and it was a little bit deeper than, when Greg wears vertical stripes because his weight appeared to be less. Let's see if we remember what we learned. You have a 100-pound child standing on a scale while riding in an elevator. It's a geek child. What does the scale read as the elevator is moving upward with a constant speed? I truly hope we all get this one right. Okay. Good, the answer is equal to B. Okay, now let's try another one. This time it's the same child on the same scale, but the elevator is arriving at the lobby, at the lowest floor, and slowing to a stop. So the question is, does the scale read less than 100 pounds, equal to 100 pounds, greater than 100 pounds? Okay. Good. The answer is greater than. Greater than. Okay. Now, what we talked about was that there were two forces acting on the person. There's the true weight. That's the gravitational force. It can only be changed through diet and exercise. It's the mass, which stays constant no matter where you go in the universe, times the gravitational field strength, which is 9.8, call it 10, here on this planet. Now, whatever keeps you from free fall, we call the apparent weight. If you're standing on a scale, it's the reading on the scale and the push by the scale on your feet. If you're standing on a floor, it's the push by the floor on your feet. If you're hanging from a trapeze bar and your feet are not touching the ground, it's the tension force that's keeping you from falling. Whatever is keeping you from free fall is the apparent weight. Now, if we have an acceleration up, as we did in that last example, you remember in the last example, the child was moving down to the lobby, but slowing down. Now, a bunch of you chose less than. You said the apparent weight was less than the true weight because you were concentrating on the going down part. Remember, the velocity is never important. It's the acceleration that is caused by the force. And in this case, the acceleration would be up. I would also have acceleration up if I were moving up and speeding up. If you got in the lobby and hit the button for the 10th floor and you took off, you'd have this situation. In either case, you're going to feel heavy. You're going to feel like you put on some pounds. On the other hand, if the acceleration is downward, you feel like the floor is falling out from under you. This is the same feeling you have on a lot of carnival rides, like a Ferris wheel, when suddenly the chair falls out from under you. That normal force that's keeping you from free fall is less than your true weight, and suddenly you feel light on your feet. You feel like you are making progress on your diet. If that value of the downward acceleration is 9.8, you are in free fall, and the normal force is 0. At this point, you are falling at the same rate that the elevator is falling, the same rate that the scale is falling, and so you're falling together. There's no normal force between you. Now, this is what is happening. Oh, you're not weightless, you appear weightless. This is what is happening in the vomit comment. We learned weeks ago that free fall is when you drop something. But it's also when you throw something. As soon as it leaves your fingers, or as soon as it leaves your foot, if you kick it, that's free fall. If you throw it straight up, that's free fall. And so you can imagine, instead of dropping an elevator, if a giant took that elevator and just chucked it like a football, the person inside would be apparently weightless. They would float next to the other things in the elevator. Well, that's what happens with the Vomit Comet. Instead of a big giant, we use the engines to provide the throw. And then they just cut the engines and go in that free fall parabolic arc. And as a result, everyone inside floats around. Okay? Now, if we go back to where we started, namely that diagram by Newton, and we look at the cannonball as it circles the Earth in path C, we ask the question, is it in free fall? Well, yeah, the only force on its free body diagram is the gravitational force, which is always pointing towards the center of the Earth. And so this is just an example of falling. And in this case, you just keep on falling and keep on missing. You're going so fast in the tangential direction that by the time you fall down to where you thought the Earth was, the curvature of the Earth has moved it out of the way. Now, because of that, those pictures of Story Musgrave floating next to the space shuttle make sense. He's not weightless. His weight is about the same as it is when he's down at home in his bathroom. He appears weightless because he's falling like he's in an elevator that's falling. Only in this case, it's falling around the Earth. Okay? Now let's talk about this problem that you voted off the island as long as we're doing this review. We're told that this elevator is moving up, and it's also slowing down. Now, the fact that it's slowing down means that the acceleration vector has to be opposite the velocity vector. And we're told that it has a magnitude of 2 meters per second every second. We pull on this rope, a string it's called, and we move this block across the floor of the elevator at a constant velocity. And there's a coefficient of kinetic friction between the floor and the block that's 0.3. And the first thing we're asked in this problem is, what direction is the acceleration? Well, that's down. The next thing we're asked is, what's the apparent weight? Well, we always start one of these problems with a free body diagram. We do a free body diagram for the block. The first force we put on any of our diagrams is the gravitational force, Earth on the block. That's going to be the mass of the block, 30 kilograms, times the gravitational field strength here on Earth, which is 9.8, let's call it 10 newtons for each kilogram. And that gives me the 300 newtons. I then ask, are there any magnets in this problem? No. But there are magnets in the homework for Friday. We finally got there. Yahoo! Aha! So, what touches the block? Well, there's the string, and the string pulls with a tension force. There's the floor, and it pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force, and I know there's a friction force because I've been given the coefficient of kinetic friction. And so that has to now, oh, someone didn't clean up their mess. Okay. every time I draw a free body diagram, I get to use Newton's second law twice. Once in the y direction and once in the x direction. In the y direction, my diagram should screen down. Now, one way to do to work these problems is to just ask how big is the screen. And that's always given by F net equals ma. I've got 30 kilograms accelerating at 2 meters per second squared down. My screen should be 60 newtons down. And in order to make this screen down by 60 newtons, this would be 240 newtons. The other way to do it is to be more careful to actually expand out Newton's second law. In the vertical direction, I have a normal force by the floor on the block, and it's up, so it's positive. I have the weight force of 300 newtons, and it's down, so it's negative. That's equal to the mass of the block, which is 30 kilograms. The acceleration is down, and that's the negative y direction, so that's negative 2 meters per second squared. So this is going to give me a normal force by the floor on the block. If I bring this negative 300 over to the other side of the equal, it becomes positive. And then I've got 30 times negative 2 is negative 60, and that gives me 240 newtons. If I do it with the math, I have to be very careful to get the minus signs in the right place. If I just use my gut, I just say, hey, that up force has to be less than the down force, because this thing has to scream down. And I better have 60 more down than I got up. Either way you do that, you get the right answer, and we'll be happy with it on the exam. Now in the x direction, there is no acceleration. It's moving at constant speed. Okay? And so that means that when I add up all these forces, I have a tension force, string on the block. It's to the right, so it's positive. I have a friction force, kinetic friction by the floor on the block, and it's to the left, so it's negative. And that's got to equal 0. Well, that's what I knew. I knew that the diagram had to screen balance. Now, the way I figure out how big those forces are is I use the fact that this friction is the easy kind of friction that always satisfies this formula as long as the indices are the same between the friction and the normal. So if this is the floor on the block, this has to be the floor on the block. Now in this problem, there's only one normal force, but in a decent problem on a decent exam, your free body diagram is going to have at least 3 normal forces, okay? So in this case, it would be 0.3 times 240 newtons, or 72 newtons. So if I come down here and plug in 72 newtons, the tension minus 72 newtons equals 0, and that gives me that the tension, if this is 72 newtons, this is 72 newtons. Now the last part of this problem asks, what if you were pulling it across that floor at a different speed? Doesn't matter. The friction force is independent of the speed at which the object is moving across the surface. And so if the friction force doesn't change, and I'm always pulling it at constant velocity, I always have 0 acceleration, so the tension would always be 72 newtons. Now I'd have to pull it harder than 72 newtons to get it up to speed, whatever that speed was. But once I got it up to speed and I wanted to keep it at that speed, I'd pull exactly with 72 newtons. Okay? Check that your neighbors on the bus, that they could do a problem like this on the midterm next Thursday. Oh, it's coming up. Next Thursday. Last day I told you about that Tower of Terror at Disney World. The first time that my family went on that, it was brand new, and it was the popular ride at Disney World, and there was a long line. And they would open up these doors and drop you and then send you on your way. Our youngest was too young to go on the ride. He was afraid. And so it was years later when we went, and it wasn't that popular anymore, and there wasn't a big line. And my son decided he was old enough to go. But he was a little timid about it. And constantly throughout the ride he was asking me, "Are we going to drop now, Dad? Are we going to drop now, Dad? Are we going to drop now, Dad?" And I kept telling him, "No, we don't drop till they open the doors. No, we don't drop till they open the doors." Well, they changed the ride. And they get you up there and they drop you in the dark, and then they pull you back up, and then they open the doors and drop you again. And so my son to this day thinks I'm a liar. So he's not wrong. Okay. I have a pretest for you because you love them so. This pretest has two sides. But it shouldn't take very long. On the back side, there's what's called an Atwood's machine. An Atwood's machine is just two masses connected by a string hanging over a pulley. There's a very famous old physics joke that goes like this. The grad student comes to the professor and asks, "Why do they name this an Atwood's machine? It's just two masses connected by a string over a pulley." The professor answers, "You misunderstand. This machine saves thousands of lives every year." The grad student says, "How can that be? It's just two masses connected by a string." He says, "But it keeps the weaker students out of medical school." It seems like every year they have some variation of an Atwood's machine problem on the MCAT. If you want to be a doctor, you should know how to do it. I didn't say it was a funny joke, I said it was a physics joke. As long as you get page 2 done by Friday, we're good. Okay? So let's talk about that page 1. With your clicker, tell me how you answered this question. The acceleration of book A is less than, equal to, or greater than the acceleration of book B. How did you answer that just now? Okay. Good. The answer is equal to. Now, folks, the people that did not put equal to, for the most part, tend to have a formula attached to their reasoning. You don't need a formula to argue that they have the same acceleration. They're moving together. If we tie your bumper to my bumper of our cars, and if you go from 0 to 60 in 5 seconds, so did I. Or one of us lost a bumper. Okay? As long as we're moving together, we're speeding up together. Now, our reasoning here involves that string. And the characteristic of the string that we care about is that it doesn't stretch. It's inextensible. It's not a bungee cord. And so when book A goes to the right by 1 inch, so does book B. They move as one unit. Okay, now let's answer the next question. And that is, the force exerted by string 1 on book A is less than, equal to, or greater than the force exerted by string 2 on book B. Tell me how you answered that question just now. Okay. Now here we're kind of divided. It's either less than or greater than, or maybe even equal to. This is truly a pretest for those of you who have not been to the tutorial yet. My guess is that, and my hope, is that those that have already been to the tutorial yesterday and this morning are the ones that got the right answer. We'll talk about the right answer after everyone's been to the tutorial. Okay? For now, it's just a pretest. Let's talk about equilibrium. I will introduce the topic with this cartoon. A lot of the other school bus drivers complain about kids fighting and fooling around on the bus. Phooey, I never have any trouble. If you just go fast enough, they stay pinned to their seats. Now, all of America laughed at that cartoon, but not all of America was laughing for the right reason, okay? If you go really, really fast, are you going to pin those kids to their seat? No, you can go 1,000,000 miles an hour. If it's a constant 1,000,000 miles an hour on a smooth road, they don't know they're not in their living room. You got to accelerate to pin those kids, okay? That's what you got to do. Now, when I talk about equilibrium, it's the same as talking about balance. If I lost my equilibrium, I've lost my balance. And the definition of equilibrium can either be that all the forces on the object are balanced, there's no net force, or you can define equilibrium as something that has zero acceleration. And I hope everyone sees that those are exactly the same thing by Newton's second law. Now, some of you are architecture majors. I'm sorry. Those of you that are architecture majors, they're going to start to look more and more haggard as the semester goes on. They have projects that go on for weeks. They don't sleep. They don't bathe. We'll know who they are. Okay? But many of the classes that you will take as architecture majors involve what's called static equilibrium. Because when you're building a house, you would like the house to not accelerate. Unless it's a mobile home. So you're going to be doing a lot with these equilibrium ideas. Now, let's look at some examples. A rocket ship has lost all of its thrusters and is now hurling helplessly out into deep space at a velocity of 5,000 meters per second. Is this rocket in equilibrium, yes or no? Yes. Yeah, if it's a constant 5,000 meters per second in a straight line, that's zero acceleration. Here's another one that we've encountered before. Jeff is trying in vain to push a large freezer of elk meat across the garage floor. It's a Montana problem. The mass of the freezer, including contents, is 250 kilograms. The coefficient of static friction between the freezer and the floor is 0.8. Jeff is pushing with a horizontal force of 1,000 newtons, but the freezer will not budge. What is the magnitude of the frictional force acting on the freezer? And you've got these formula on the front of your exam. So tell your neighbor, what is the magnitude of the friction force? Okay. If you reach for a calculator, you're confused. Okay? There is no calculation necessary. This is just balance. I mean, Jeff pushes with 1,000 newtons one way and it doesn't go anywhere. The friction must be 1,000 newtons the other way. It's that simple. Now, those of you that reach for the calculator, you're using this formula right here, which is not a formula, I repeat, is not a formula for static friction. It's a formula for the maximum value of static friction. If I had asked, how hard will Jeff have to push in order to break these surfaces free of each other and get this thing to start moving? Then I would plug into that formula, and the answer would be 2,000 newtons. Jeff would have to push with 2,000 newtons to get this thing to start moving. Okay? Now, last week we had this pretest where you were asked to draw free-body diagrams for a rock and a crate. The rock was riding on top of the crate and everything was being pushed across the floor at constant velocity. Okay, that's the key. Equilibrium. Now, the surfaces are all rough. The floor is rough, the crate is rough, the rock is rough. And so let's draw the free body diagrams. We always draw the easiest free body diagram first. The object that's touching the fewest other objects. Well, that's the rock. The first force I put on there is always the gravitational force, Earth on the rock. I then ask, are there any magnets in this problem? Not yet. What touches the rock? The crate. Does it push or does it pull? It's not a string, not a rope, not a chain, so it pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Here's the thing. If there's a friction force, there's only one friction force. I've only got one more force in my quiver here. Okay? That friction force can either point to the right, to the left, or it can be zero. Tell your neighbor what I want this friction force to do. Point right, point left, or be zero. Talk to your neighbor. Okay. It's not hard. I want that diagram to scream balance. If I put a friction force to the right, it screams to the right. If I put a friction force to the left, it screams to the left. That won't work. The only thing left is zero. And that's what the friction force is. Now these are rough surfaces. The nooks and crannies of the rock are meshed with the nooks and crannies of the crate. But why is there no friction? Well, let's imagine greasing down the top of the crate and greasing down the bottom of the rock. If I push that crate from rest, if I start it from rest, the rock's going to slip off the back and hit me on the foot, right? If I want to start this up from rest, I'm going to have to hold that rock on top of the crate. I'm going to have to push them both. But once I get them up to constant velocity, I can take my hand away from the rock and the rock will just keep going. That's Newton's first law, or Galileo's law. Once a body's in motion, it wants to stay in motion at constant velocity. The nooks and crannies between the rock and the crate are still enmeshed, but they're not pushing on each other. Because both things want to just keep going at that same speed, they just travel together without either one pushing on the other. Okay, in the horizontal direction. Now let's draw a free body diagram for the crate. The first force I put on any diagram is the gravitational force. Then I ask, are there any magnets? No. What touches the crate? Well, the rock. And if the crate pushes up on the rock with a normal force, by third law, the rock will push down on the crate with a normal force. The other thing pushing on the crate is the floor. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. In this case, we can hear the scraping between the bottom of the crate and the floor. So we know that it's a kinetic friction. Because this crate is moving at a constant velocity, and I only have one remaining force, the push by the person, it's got to be equal to that friction force. And remember, that's how we found the magnitude of the kinetic friction force last week, is indirectly through the push by the person. Okay, now, in this pretest, careful folks, people lose points on the next midterm here. On this pretest, you were asked to find the third law force companion for each force acting on the rock. Now, on exam situations, what we find over and over again is people doing this. They say, oh, those two are companions, tick mark, tick mark. And if I had asked you if there's any force pairs on your diagrams, label them, you would get full credit. But in this case, I asked for each force acting on the rock, find the companion. And so you would only get half the points if you did that. To get the rest of the points, you would have to identify the companion to that weight force, which would be the rock pulling on the earth. So you need to carefully read the problem and see which way it's worded to see what's required for full credit. Okay? Questions on that pretest? Yes.
Going back to your example of being like in a Lamborghini, you're sitting in the Lamborghini.
Uh-huh.
You're moving at the same, like you have the same.
With the Lamborghini.
Right. So is this just different because it's constant speed versus you were speeding up?
Yes, if the Lamborghini is speeding up from 0 to 60 miles an hour in 2 seconds, so am I, because I'm moving with the Lamborghini. In this case, because the crate has 0 acceleration, so does the rock. They're moving together, so they both have the same acceleration. In this case, it's 0. Okay. I would not pay lots and lots of money for this kind of vehicle. It's boring. Okay. Now, this is a problem from the old textbook, Cutnell and Johnson, that cost $250. I used to assign it every semester. A supertanker, mass big, is moving with a constant velocity. Its engines generate a forward thrust of 7.4 times 10 to the 5th newtons. Find the magnitude of the total resistive force exerted on the tanker by the water in the air, and find the magnitude of the upward force exerted on the tanker by the water. Now, every time I assigned this problem, I was guaranteed to have a long line of students outside my door. And nearly every student that walked in my door said the same thing. I have no idea how to start this problem. Well, that's just a lie. You're just looking me in the face and lying to me. Because you know how to start every single dynamics problem. How do you start a dynamics problem? A free body diagram. A free body diagram. Okay, so we draw a free body diagram. The first force we put on it is the weight force. I take that mass that was big, multiply it by 9.8, call it 10, and I get that many newtons. I then ask, are there any magnets in this problem? Nope, they're coming. So what touches the tanker? Well, the water. Now, how do we account for the water? We're told that there's this thrust force caused by the engine on the tanker. Now, if we think about that, that's the engine turning the propeller. And the propeller is shaped such that it pushes water back. Now, if the propeller is pushing water back, By third law, the water is pushing the propeller and hence the boat forward. Either way you look at it, it's a forward force that is 7.4 times 10 to the 5th newtons. Now, we also know that there's a force by the water up. That force has a name. It's called the buoyant force. We're not going to get to it before this next exam. We're going to hold off and wait till towards the end of the semester to talk about it. It's one of the most exciting, richest of the forces. It'll be fun. But we don't need to understand it inside out to know how big it is, do we? No, we know how big it is. It's this big. And likewise, in this problem, they lump together all the friction, whether it's due to the water pushing against the front of the ship or the wind pushing against the part of the ship that's out of the water. That's a strange way to lump your friction forces. I wouldn't do it. I don't use their book. Okay? You don't pay $250. But still, without agreeing on that labeling, I know how big this force is, don't I? Because this tanker's going at constant velocity. This diagram has to scream balance. So this force has to be that big, and this force has to be this big. Okay? So it's really not that hard if we just follow the recipe. Now, many, many years ago, when I was your age, if you can imagine it, I took a class from Stephen R. Covey. Now, Stephen R. Covey was the most popular professor on our campus. He went on to become a very famous author, making millions and millions of dollars. There are baseball stadiums that are named after him. And anyway, he was popular because what he would do is he would motivate. And he would motivate by telling stories. And he taught in this great big lecture hall that just went on forever. It was where they had plays and operas and everything. And it was huge, and it was always packed. And he always had 4 TAs that were just in charge of keeping his cable, his cord untangled. Because this was back in the olden days when microphones had cords. And this guy was intense. I mean, his eyes could burn through you. And he was bald as a billiard ball. And he was always just rubbing his head. I think that's how he became bald. And he couldn't stay still. He was all over the room telling his stories. And we were loving his stories. It went on, after he taught for some years, he would give inspirational talks to corporations. And they'd pay him hundreds of thousands of dollars to come in and tell his stories. Well, one story that made an impression on me was a story about a woodcutter. Oompa, 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 sawing down a tree. Oompa, oompa. And along came a hiker, and the hiker said, "What are you doing?" Oompa, oompa, I'm sawing down this tree. Oompa, oompa. The hiker said, "Whoa, how long's it taking?" Oompa, oompa, I've been doing it about 6 hours. Oompa, oompa. Whoa, how come it's taking so long? Oompa, oompa, my saw is really dull. Oompa, oompa. Whoa, why don't you sharpen the saw? Oompa, oompa, because I'm busy sawing down this tree. Oompa, oompa. Didn't say it was funny, I said it was meaningful. Now, what does that have to do with you? Next Thursday, on your exam, some of the problems will have boxes where you will draw your free body diagrams. You will be offered lots and lots of points for your free body diagrams. Put the diagram in the box, get your points. Most of the problems on the exam will not have a box for your free body diagram, will not require you to draw a free body diagram. For those problems, you do not, I repeat, you do not have to draw a free body diagram unless you want any hope whatsoever of getting the right answer. Every single dynamics problem starts with a free body diagram. If I don't give you a box, turn the page over, use the back of the page. But if you think you are saving time by not drawing that free body diagram, I've got some trees for you to saw down with my saw, okay? Now, let's spice this up. Suppose instead of moving with constant velocity, this tanker moves with a constant acceleration, not a big one, but an acceleration still the same. The mass is the same, the thrust of the engine is the same. If I look at that Freebody diagram, what has got to change? Yeah, that friction force has to get smaller. Somehow I need to streamline that boat so that either the water's not pushing as hard on it or the wind's not pushing as hard on it. Now, I have here a problem. This problem has 6 parts. I gave it on an exam 23 years ago, my first semester teaching here. I had a large, huge class with 2 sections, about 350 students. And nearly all of the students got parts A and B right. Most of the students got part C right. But then they started falling off the bus, and by the time we got to the last part of the problem, only 5 students got it right. So ever since then, I've called it the gauntlet. And I want you to run the gauntlet and see how far you can get through it. You make it all the way to the end, you're ready. You're going to do just fine next Thursday. If you don't, we got some work to do. Now I'm going to go over this problem next week, but that's not going to do you any good at all. I need you to go through this problem as if it were an exam problem, just so that you can see where you stand, how ready you are. Tomorrow I'm also going to post 2 sample exams, 2 sample midterms, as well as their solutions. And you can measure your preparation against them as well. As soon as you have got a copy of this handout, you're free to go, and we'll see you on Friday.